Today I'm going to talk about parallel transport, and I'm going to talk about parallel transport in Riemannian geometry. What does that mean? We're going to move a vector in a curved manifold. So if you move vectors, and a vector can be defined as such, right? You have a vector v with components v mu and base vectors e mu, right? And if you have this vector in normal Euclidean space, you can move this vector at will and nothing will change, right? If you have a vector, for instance, and you move it in Euclidean space, there's a vector here, v, you move it in Euclidean space, you have your EY vector base vectors here and your EX base vector here. So your vector v can be expressed as Vx, right, where this is the Vx, that's the Vx part, and the Vy part is over there, that's this piece, okay, that height, and the Vx is that height. So you get your vector v equals Vx Ex, where Ex is the base vector, plus Vi y Ey. Okay, that's how you represent a vector in Euclidean space. If you move that vector to another location, for instance here, you still get exactly the same components and exactly the same base vectors, because these are not changing in Euclidean space. Ex and Ey will not change, and so will Vx and Vy. If you parallel transport this vector, it will not change. In curved space-time, that's not the case. If you do this in curved space-time, not only the vector components will change, but also the base vectors will change. They will both change. So in Euclidean space, it's perfectly fine to define differentiation with respect to vector components as such. And you just say, okay, it's kind of like differentiating a function, right? There's no difference here. You have the differentiation of v mu, which are the components of the vector, times x mu, times differentiated towards a certain direction, right? X, y, or z, or something else. And this is just a normal definition of differentiation. X plus delta x minus x divided by delta x, right? You can also do that with a function here. You can say a function x plus delta x minus fx over delta x. That's just the definition of differentiation. That's not possible in Riemannian geometry or in curved space. The reason is that the base vectors change, right? And as a side note, I use implicit summation here. I use the Einstein convention here, where I implicitly sum over over the components and over the base vectors, okay? And I did that here as well. So if you have a v like so, you can define this as v mu e mu, right? Where v mu is Vx and Vy, and e mu is Ex and Ey. And you do that also in curved space-time, okay? So that's the Einstein convention. Now, if you want to transport a vector in Riemannian geometry, in a curved space manifold, you not only have to take care of your components, but you also have to take care of your base vectors. And in order to do that, you would like to see that two rules are being met. You want to make sure that if you transport your v mu vector here, the vector components of this vector, you transport them to a new location, so you get the v tilde, right? If you transport this vector to x plus delta x, where it was originally at x, you get new components called v tilde mu, right? So going forward, that's what we will mean by v tilde mu here. And if you subtract that from v mu here, you would like to see them proportional to delta x. So if you move in the r direction, it needs to be proportional to delta r, and we will see that later in an example. And if you move it in the phi direction, it better be proportional to phi, right? To delta phi here. What you would also like is that it is linear. So if you have a vector v at position x and there's another vector w at position x, you add them up, you parallel transport them, right? And you get a new vector there, or vector components there. It better be the same than that you first transport v, then transport w, then add them up in the transported location x plus delta x. That better be the same. And that's what's reflected here. And if you adhere to these two rules, you can essentially set something up like this. So your parallel transport of the vector v mu at position x, and you parallel transport these vector components to these new x plus delta x location with v mu tilde, that's identical to v mu minus some linear combination of delta x's and your original vector, okay? And this linear combination is reflected in all these numbers. And these numbers are chosen such that the base vectors that also move when you move from point A to point B in a curved space-time, that difference is also being captured. Okay, so that's important. For completeness, I give you the definition of Christoffel symbols, which I'm not going to use today, but I'm going to derive this in a different video. But just for completeness, that you can see that it only depends on the metric, for instance. Okay. Now, so a useful definition of a differentiation in a covariant way, and it's called covariant differentiation if you differentiate on a manifold, on a curved manifold, whereas you call it normal differentiation if you do that in a flat space-time. Okay, so this covariant differentiation is defined as follows. You take a mu at x plus delta x, original vector, you subtract this transported, this parallel transported vector at x. So you have a vector v mu, vector components at x plus delta x, and you parallel transport a v mu at x, you get this tilde one, right? So you get those new components, you subtract those from each other. Now you can subtract them because they are at the same location, right? This is at location x plus delta x, that is at location x plus delta x. You cannot really do that here, because if you have curved space-time, the base vectors also change. So you cannot really compare this with this. You can compare this with this, however, because you parallel transported this vector and you got this as a result. So subtract those with delta x and you get your covariant differentiation. Yeah, and if you fill this form out in here, you get this. And this is really covariant differentiation. And that's also denoted with a delta sometimes, right? If you covariantly differentiate with a nabla, if you covariantly differentiate with respect to x alpha, you usually write it like this, okay? So that's the first. So now let's take a look at an example. How can we calculate these Christoffel symbols, or these connection coefficients? So these symbols here are called connection coefficients or Christoffel symbols, right? These numbers over here. And they are called that way because we are looking at the Riemannian geometry. If you do Riemannian geometry, you will end up with connection coefficients that are Christoffel symbols. Okay. So we have these, this example which we are gonna explore to see how these connection coefficients can be calculated without using that formula that I gave. So we're not going to use this formula, we're just going to use it by looking at the definition and see what happens in a picture. Okay, and I think that's very insightful, and it gives you a lot of insight in what parallel transport really is and what covariant differentiation really is. So we start with a point x mu, and we do that in flat space-time, but we use polar coordinates. And you will see that some of the components will be non-zero because of that. So we have x mu, which is r cosine phi, r sine phi. That's just a polar coordinate. That's just this location in polar coordinates, okay? R phi. That location can be reflected as such if you embed it into Euclidean space. The metric you get out of this is this, and I'm not going to explain this here today, But if there are a lot of questions on it, I can do a separate video on how to calculate this metric. But this metric is quite important because that tells you how space really morphs from location to location. For instance here, because there's a 1 in front of it, GRR as a consequence is 1 here. So if you move in the R direction, there will not be any difference with the VR factor, and we will see that later. But in the phi direction is definitely a difference because of the R d phi and not just d phi. Okay? So we have our vector V, which is VR ddr plus V phi dd phi. Okay? We're going to parallel transport this vector into our new location at R plus delta R. So we get a V tilde R, ddr in the new location, R plus delta R. So we move from this vector, V, will be moved from here to here. Okay, plus V tilde phi times dd phi in our new location. Okay, and we're going to find out what these components are. We're going to calculate those. Let's start with what it is here. So VR, so let's start what the components are in this, for this vector here. So in the direction of R, ddr is actually in this direction, right? So if you would write the base vector here, you get a ddr that's in that direction, and then perpendicular to it here you have a dd phi. Okay, dd phi, and don't mind the lengths, but that's in that direction and the ddr is in that direction. So we're now going to calculate what VR is, and if you look at it, it's in the direction of ddr, so it's just the projection of this V vector on this line, which is V cosine theta. Okay, and that's what you see here. And because dr squared equals 1, we're already okay here. Okay. For V phi it's a little bit harder to see. You can do exactly the same. The dd phi is in this direction, so you get a V sine phi. But you have to divide by r, and that looks a little strange, but it does make sense. And let's take a look at why that makes sense. If you calculate the length of a vector that's only operational in this direction, for instance, in the V phi direction, we can do that and we can say, okay, V phi at that moment is, and let's assume that this is correct. So we say V over r sine pi over 2. And then we don't have an r direction, right? Because it's only in the direction of phi. So we have this vector, okay? And we say that, let's say that that's okay. Let's calculate the length of this vector. How do you do that? Well, you do that with phi alpha, phi beta, g alpha beta. This is the length squared of the vector. That's what this is, okay? So we fill it out. By the way, phi r equals 0, right? We stated that because in this case, specific case, just to show that this works, theta is pi over 2. So therefore, phi r equals 0. If you fill that out here, right, you get 0. If theta is pi over 2, this portion will be 0. Okay, so you get phi phi times g phi phi. Okay, and that's all you get because all the other terms are 0. So you get, you fill this one out, phi squared over r squared. Sine pi over 2 equals 1, right? So you get this times this, that's phi squared over r squared, times r squared, g phi phi, right? That's this term here, g phi phi, r squared, and that gives you exactly phi squared, right? And that's what you need because that's the length of the vector after all. The length of the vector here is indeed phi, right? So this is length squared, phi squared. So that's why you need to divide by r, right? So, okay, now we know that this is correct and this is correct. So now let's take a look at V tilde r. So now you're going to parallel transport, and that's what we did here. We parallel transport it, and you can see that this vector is exactly parallel to this vector. Why is that? Well, it's parallel transported in flat space-time, right? It's flat space. So of course this will be parallel transported that way, like you do it conventionally. If you transport a vector in a parallel fashion, you will do it like this. This is exactly parallel. So that's what we do here. So now you can already see that V tilde r, because that one has a 1 here, is not going to change. If you move in this direction, the projection will not change. So Vr will be exactly the same as it was before. Okay, for phi, that's obviously not the case. What you do there is you say, okay, we're going to do the same as we did here. So you can quickly say, okay, phi tilde equals, right, phi sine, again that projection, here, this piece, but now it's r plus delta r, because we are in our new location L plus delta r here, r plus delta r, okay? So that's our new location. This is the same as sine phi over r times r plus delta r. That's exactly the same, right? This is Vr, this piece, right? That's Vr times r plus delta r. And that's what we see there, right? And now you can say, okay, this is the same as top and bottom divided by r. So you get delta r over r. You Taylor expand this to first order and you get this, okay? So at first order, and you can do that at first order because delta r is really small. Okay, so at first order you get this. And now we have the ability to read off the coefficients from our definition that we had before. So this is our definition on parallel transport. So here you go from, let's start with r. So phi tilde r, let's fill that out. Make this an r, make this an r, and make this an r, okay? And you can already see there are no other components here, so everything has to be 0 here. If there's an r up top here, it better be 0, right? Because there's nothing there here. So the r will be 0 and the r phi will be 0 as a consequence. Looking at phi tilde, we can already see that, okay, that's phi, which we have here. So the mu is now phi. So now we're going to look at the phi terms, right? Phi in the top here. Those are the terms we're going to look at. There's only one term when it comes to phi. So this one needs to be phi also. So you fill that out, phi. That's there. It's symmetric, right? And there is a phi here. And there's a delta r here, of course. So you get the r phi term. And that gives you 1 over r. So you can immediately read off, and as a consequence, the other one is 0. So you can immediately read off your Christoffel symbols through geometry, okay? And we did this by moving into the r direction. So now as a second example, we're going to move in the phi direction to calculate the other Christoffel symbols, right? Again, we do the same. We have x mu here, we have g here. V is obviously still the same. The parallel transported one is now in the direction of phi, right? So not in the direction of r plus delta r is no longer there. This is r, and now you move in the direction of phi. You rotate a little bit like so. And that's what we did here. So you go from your original phi factor here at r phi, you go to your phi tilde one through a rotation by an angle of delta phi. If you do that, you get, of course, for your Vr and Vphi, they are still the same from this location. Nothing changed. But the phi tilde r now is rotated, right? And what is the r now? Well, r is now the projection on this one, and this line has been rotated, right? How much has it been rotated? Well, theta minus delta phi, right? So now this angle is smaller because it has been rotated by delta phi. So now you get, for the tilde version of r, phi cosine theta minus delta phi. Okay? Now you use some trigonometry and you can work it out to being this, right? It's just a product of, it's a summation of two angles, and you can work that out. And if you do that nicely, phi cosine theta is again Vr. Phi sine theta is obviously r times phi theta, Vphi. Okay, you see that over here, times delta phi over here. And now it's again in a form that you can read off your Christoffel symbols. Now you do the same for phi. If you look at how phi is being affected by this rotation, right, that's this little piece over here. So you get Vr is phi cosine, phi sine theta minus delta phi over r. Okay, r has not been adjusted. R is still the same. This is R, this is also R, so we don't get an R plus delta R here, for instance, but what we do get is a theta minus delta phi here, because that angle got smaller, okay, for the sine. If you work that out, you get something similar. Yeah, you get again phi tilde phi equals phi phi, the original one, minus a component. And this component, of course, again, can be translated into a Christoffel symbol. So again, you use your definition on these two. You can start with R. So these are the R components for this. So you fill out R here for the new R, the phi tilde R over here, which is phi R over here, plus this term. Here is a minus. So, of course, the term will be minus R, okay? Because there's a minus here and there's a plus there. So if you put a minus here on your Christoffel symbol, you will be okay. So your R phi phi term will be minus R and the other one will be 0. And similar for phi, and you will find that your phi phi R term will be 1 over R by comparing it with this formula, and the phi 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 term will be 0. Okay? Okay, I think this is a great place to stop. I hope that you got some insight in how this works, how to do parallel transport, and how to do covariant differentiation. Okay? So if you like this video, please like and please subscribe, and I'll see you in the next one.